So when people think about design thinking for blockchain, they think of mining or the consensus algorithms or the hash linking or the smart contracts. And I really didn't think they were critical. I was more concerned with how is this distributed ledger going to work in the real world, handling transactions of all sorts. Hello, I'm Paul Dowding, and in today's video, I'm going to be discussing design thinking for blockchains, or I prefer to consider it design thinking for distributed ledger technology, as that covers a broader base of solutions that need to be looked at. When people are considering blockchain designs for distributed ledgers, they're often considering or taking the available open source software or the ideas that exist, and then they try and tweak them to improve them in different ways. Whereas really what was necessary was to see what was the benefit of a distributed ledger, but then how can those fundamental properties be applied such that it met all the requirements and the holistic needs of the transactional industries. So when people think about design thinking for blockchain, they think of mining or the consensus algorithms or the hash linking or the smart contracts. And I really didn't think they were critical. I was more concerned with how is this distributed ledger going to work in the real world, handling transactions of all sorts. So I'm going to go through a list of 10 of what I called the challenges. When I reviewed what distributed ledgers could do, these were the challenges I saw that were needed to augment the current designs so that they could meet the needs of various transactional industries. So first up is the point that I made, which is these distributed ledgers have to be applicable to many different use cases. So your design has to be flexible. It actually has to be lifecycle agnostic. And that's one of the first challenges. How do you make the transfer of any type of asset generic and with the ability to be adaptable to all those different life cycles? The next challenge is related to performance, and this covers a series of factors. First one is scalability. Can the network grow? Can it handle high capacity throughput, meaning a large amount of volumes in a short amount of time? And then also, can it operate quickly? And that's low latency. And there's a difference between high capacity and low latency. And the example I can give is if you have a dishwasher that washes 60 dishes in an hour, right? On average, that's a dish per minute, but the latency for each dish is 1 hour. The third challenge is confidentiality. Now, this is made hard because by definition of a distributed ledger, we are sharing all the data with everyone who participates in that network. And it's not just about confidentiality around identity. It's also confidentiality around transacting patterns. Because as you transact through a network, you may leave clues which are not directly identifying you, but indirectly identifying you by activities. The fourth challenge is actually the validation method of the distributed ledger, which has to be achieved is how do all the nodes in the network validate the ledger that's generated between them. At the moment, there's only really two main methodologies, mining and consensus. There are some other slight variations like proof of stake and other ones, but they're more or less consensus driven or competition driven. And the problem they have is that they really don't meet those performance requirements of near real time, scalable, high capacity. So we need to have a distributed ledger validation technique that meets that requirement. The fifth challenge is actually related to that issue in that it's both the solution has to be memory scalable and also computationally linearly scalable. Now, I've done some other videos on memory scalability and how consensus doesn't scale, so you may want to look at those for the details. but having memory scalability and linear scalability as far as generating and validating transactions is critical. The sixth challenge is one which I call contingent transactions or contingent transfers. And this is where someone pays money for shares, or in an FX transactions, you pay euros for dollars. So you've got two assets going in different directions. But the idea of being able to do two legs of the same transaction simultaneously without settling one, without settling the other, is definitely a challenge that any distributed ledger has to meet. And the seventh challenge is related to those different transactions, in that the transactions may be loans or pledging of collateral. In fact, there's a whole set of transactions that rely on financing or obligations, meaning I will transact with you in the future, but I'm not transacting with you right now. And that also brings up the concept of having a future dated transaction. Today we can accrue interest. How would you do that on today's blockchains? This is a critical element to how industries or obligations in supply chain, or anything in terms of records management of expectations or dates, all of them would have to be recorded as future dated transactions. So the idea of obligations, so financing and future dated transactions, is a key design challenge for the blockchain. The eighth challenge is one which I made a separate video about, and it's interoperability. And most people think of this as being able to interoperate between different blockchains, whereas I think that's a false premise. What you really need is the ability to interoperate with current markets, because people are not going to be transacting in your distributed ledger with all their assets day one. So you've got to be able to settle within your network and outside your network. And the other aspect of interoperability is the longer term goal that once we have a consistent transaction protocol that different networks are using, they have to be able to transact network to network. The ninth challenge is regulatory compliance and reporting. Regardless of what life cycle event you're recording on a distributed ledger, there's usually a requirement to either comply with regulations or prove the compliance or report on certain data within the network. So all the network has to be able to do is accommodate that requirement relatively easily and hopefully in near real time. The 10th and last challenge is to incorporate double entry accounting into the immutable record. Even if you're not dealing with financial assets, there may be a requirement to record them and account for them and even reconcile them. So without double entry accounting, the task becomes much more challenging as well as onerous. So double entry accounting within a distributed ledger is absolutely essential. So to finish off, let's do a whiteboard summary of the 10 design challenges. The order we discuss them, design thinking summary goes as follows: lifecycle agnostic, the performance, confidentiality, the distributed ledger validation methodology, memory and linear scalability, having contingent transactions, being able to handle financing and future dated transactions, interoperability with current markets and other networks, regulatory compliance and reporting, and double entry accounting. And I'll leave them here just for a few seconds so you can review them. So there they are, there's the 10 challenges. I'm not saying they're the full set of requirements for a distributed ledger network, but there's certainly a very, very strong foundation. Well, there you go. So I hope you found this video useful, and the questions will help you in your assessments of any distributed ledger technology solutions you're considering. So thank you again for watching, and if you have any questions or comments, please leave them in the comments below.